So there's 7 people. They're going to be in some kind of order. How many ways can we put them in order? That's the question.
5,040.
You think 5,040? Okay. Let's, I guess. How did he get 5,040? What did he do?
7 times 6 times 5, etc.
7 times 6 times 5 times etc.
Yes.
Times 0?
No.
No, not that much etc. Now what do we call that? 7 what?
Factorial.
Alright, nice. And the reason that we do 7 factorial is because for the first person, there are 7 possibilities for that first person. Since we're going in order, there's 6 possibilities for the next person, because one of them's already gone. 5 possibilities for the next, 4 for the next, 3 for the next, 2 for the next, 1 for the next. Because we're taking them one at a time, it would be 7 choose, or 7, order matters, so 7 permuted 1. So it would be 7 permutation with 1. And so this would be just 7 factorial over 1 factorial, I believe.
Why is it 1?
Because they're taking it one at a time. One at a time. Okay, so again, we're looking at how many ways these things can be ordered. That's 7 factorial, 5,040. Good. I have now. We're going to change it a little bit. I have a 6-sided die. We're going to take that 6-sided die. Boom. Roll it.
Boom.
What are the chances that I'm going to hit a 5?
1/6.
Why is it 1/6? What's the 1 represent?
The 5.
Okay. Yes, I know. I'm waiting for it to get quiet. Out of, what does the 6 represent?
6.
All the possibilities.
Yeah. We would consider this a success. Hitting the 5 would be a success. Out of the total amount of possibilities.
I thought that was a trick question.
Oh, really?
Yeah.
Because it's so easy, huh? Yeah, right? You're just smarter than you think. Alright, so now, I have to choose a student to go buy the class Starbucks. So I'm going to go through, I'm going to close my eyes, I'm going to go, you, go buy Starbucks for everybody. What are the chances that I choose a boy?
Wait. How did there's 33 people or 34?
I don't know. How many
We
go?
got 33.
Did you count?
34, yeah.
What'd you get?
33.
Did you include yourself?
Oh, wait.
Alone is not
The
here.
class is us?
Yeah. That doesn't
Oh.
matter.
What?
No, it's not.
What does it say?
You included TA.
What does it say?
What are the chances that you boy?
No. What does it say? I have to choose a...
Student.
So we have to count all the... in the room.
Is it TA?
No. Not
Is
TA.
he a student?
No, not
I mean,
her.
She may not be taking Algebra 2, but she is a student. So our total has to be the amount of students that we have.
She gets a grade for TA.
What's that? She does get a grade for TA. And so technically, since she's a teacher's assistant, that's what it means, we use students as assistants. So she's technically a student.
So why would you put a student instead of saying TA?
Because I may not want her to buy Starbucks for everybody. She might spit in my drink. I don't know.
As long as we don't include her.
But I could choose her. She is a student.
Okay.
Again, I'm choosing a student to do
If
it.
you're not arguing TA, then you might as well just not include her.
Well, what her role is in the class doesn't matter. The fact is she's a student. Okay, so I have to choose a student to buy the class Starbucks. What are the chances, what are the odds, that I choose a boy?
1/2.
So I heard 50% earlier and I heard 1/2 now. Why, what fraction is going to give you 50%?
17/34.
How much?
17/34.
Why 17?
Because there's 17 boys.
And 34 what?
Students.
Students, good. So 17 boys out of 34 students. That's important because you need to know the total, and the total is given to you usually in the question. given to you in the question. So you have to know what you're counting. So it's 34 students, happens to be 17 boys, that gives you 1/2 when you reduce it, which gives you 50%. I swear I did not work it out that way. It's pretty cool. What are the chances that I'm not going to choose a boy? 1/2, same thing, 50%. I know it, right? So 17 not boys. Now, well, not necessarily. I mean, without getting into too much science, just because somebody is not a boy doesn't necessarily mean that they're a girl.
Wait, what do you mean?
Oh, you just got
What?
Again, without getting into too much science,
Math is a science.
not boys, because actually not.
Oh!
Alright. So,
Teacher sitting down.
again, the question was, or better yet, the question was not, what are the chances that I choose a girl? The question was, what are the chances that I do not choose a boy? Because there could have been a third possibility. And so whatever that third possibility, whatever it is not a boy. Yes?
Are you talking about gender identity or biology?
Biology.
Okay.
Because
What kind of student?
if we're talking about gender identity, interesting. Then that would get into more psychology than anything else. Because somebody could, again, still not identify as a boy, but not necessarily be identified as a girl. So it works both ways. Okay.
We are getting too much science.
It's a soft science. Alright, so that's it for the warm-up. Go ahead and get out a piece of paper for some notes. I'm going to write one more question here.
May the forces be with you. Wait, that's the prosperous thing.
Live long and prosper.
Yeah.
The Force be with you as in Star Wars.
Yes.
Oh, I switched it. Wars and track.
Your camera's not ready.
It's okay. Okay, go ahead and write down those questions, please. At least the first one. Yeah.
You know what? Maybe.
All of that? Yeah, so write down at least the first one. We're going to end up doing all three. Okay. I have a 52 right there.
Yeah, for the second part, you have 7 friends.
You got 4 friends out of the 7 that are performing in number 1. Oh, we're going off of number 1. So number 1 is second question. So the second and third questions right there, you have a friend and now you have 4 friends, those are both based on number 1 from the warm-up. So it's the same performance as is happening in number 1 in the warm-up. So we're just extending that idea out.
So only write down the one that's probably.
So 9 is any 9 of any suit, right?
Any suit, yeah. Any suit.
Wait, in the cards, is there like Jack and Queen also?
Yes. Jack, Queen, and Kings, all three suits.
Wait, those aren't even numbers though, right? Those don't count as evens or odds.
What?
Jack, Queen, and Kings.
Yeah, face cards don't count as even or odds. They do not count.
What's an ace? Oh, ace is like 1, right?
It can be one, not a base card. Yeah.
5,000 gold.
See you later sometime.
Yeah.
For you.
Yeah. 1, 2, 3, all the way to 52. I'm really good at Uno. Because when we get down, we're like, Uno! And I actually speak Spanish, so I know what I'm saying.
I mean, don't mess around.
Just want to get a little face shot.
Break stuff. Photo, what is it? What do they call that? Photo bombing? Photo bombing is lesson. Alright. Now that you've got it written down, now let's talk a little bit. Okay, so I've got a deck of cards. Got my Scooby-Doo cards again. Remember there are only how many cards in the total deck? 52. Alright, so no jokers because I took them out. Otherwise they would be how many? 4, right. But then they wouldn't all be in the same suit. So we have a 52 card deck. Okay? 52 cards. And I want, oh by the way, a couple of things. There's some vocabulary that we need to talk about. First thing, there's a couple of different kinds of probability. Okay, so here I said, what are the chances? I'm going to start changing that word, chances or odds or whatever that, to probability. Okay, that's a mathematical term. So we're going to be dealing with probability. We're going to be dealing with a couple of different kinds of probability, 3 to be exact. There is theoretical probability. There's theoretical probability, which has to do with every possible theoretical outcome and every possibility. Okay, so that's theoretical probability. There's experimental probability, where we actually do a bunch of stuff, we actually do a bunch of trials, and then we look at the results, and we base our probability off of those results.
So that's not always accurate though?
Not always accurate. No, not always accurate for prediction, but it is accurate when you're dealing with what you've already seen and furthering patterns. Then there's geometric probability, and geometric probability just has to do with area. And so that's kind of easy. There's 3 kinds of probability. The majority of the type of probability that you'll see will be theoretical probability. For example, the 52 card deck is all based on theoretical probability. So, what's the probability of getting a 5 of clubs on a single draw?
1 out of
Exactly. There's only one of them out of the 52 cards. What about the probability of getting a heart?
13 out of 4.
Okay, so I hear a couple of different fractions. I heard 1/4. And where did 1/4 come from?
2/8.
13 out of 52. Could have been 2/8. Could have been 2/8, and we would have just kept building it up until we got to 13 out of 52. Why is there 13 out of 52?
Because it's divided by 4.
Because yeah, there's 13 hearts, because the whole deck is divided up into 4 suits. So 13 of those cards are hearts out of the 52 total. Okay, so 1/4. What about the probability of getting a 9?
That's a Q.
So yeah, I heard 4/50 seconds, yeah, and that reduces to 13th. Okay, so you always want to reduce these fractions. Ooh, here we go. What about the probability of getting an even diamond? It's going to shine really bright.
5 out of 52.
4 out of 52? Okay, so I heard 1/24th. I heard, let's see, I heard 4/50 seconds, 1/24th. Any other guesses? You think it's 550 seconds? 5? Well, I don't know. I mean, so
4.5.
you would think, but wait, there's 13 hearts. How come there's only 5 even numbers?
Because there's the other base cards aren't even or odd.
Oh, the what kind of cards?
Base cards.
Ace cards. So yeah. So we're really only looking at the 2 of diamonds, 4 diamonds, 6 of diamonds, 8 of diamonds, 10 of diamonds. Skip the jack. Do we look at the queen of diamonds?
Ace. Oh no.
Ace is 1.
Yeah.
So no queen. So yeah, it is only 5. So it's only 5 out of 52. Okay. What about the probability of getting a face card?
That's
52.
16 out of 52. Is ace face?
Ace is not a face card.
16 out of
16?
52.
12 out of 52?
Yeah.
16 out of 52? 3
Oh.
Okay, so there's a lot of fractions flying.
Oh.
Again, how many cards do we have total?
2.
2. Which ones are considered face cards?
Queens,
Jack.
kings, and jacks.
Queens, okay, queens, kings, and jacks. How many sets of those do we have? 4. So 3 times 4 is? Yes, 12. And that reduces to?
6.6, and then 3.
0.23076.
2, 3.
0.76923.
Okay. So we'll leave it at 0.23, or it could be 23%. 23%. What about the probability of not getting a 3?
12 out of 13.
Oh, so that's reduced. So she got 12 out of 13.
48 out of
What would that be out of 52?
52.
You think it's 48? Is it?
12 times
Yeah.
48.
Oh, okay. Watch your language. So 48 out of 52 reduces down to 12 out of 13. Very nice. And that's the probability of getting anything except for a 3. Okay? So you can see that these kind of work inside of a kind of a boundary. They're always in between 0 and 1. Your probabilities are always going to be between 0 and 1. So just be aware of that. Okay, so you will never have more than a 1.0 probability of doing anything because that's more than 100%. You can consider these percentages. Just like that 0.23 could be considered 23%. Yeah. All right. So again, that's theoretical probability. We're going to continue with theoretical probability through these 2 problems. Then we're going to switch to experimental and geometric probability. So first thing, you've got a friend that's going to be performing in this show. Okay, so I'm going to put the cards in. We have a friend that's performing in that show. How many, let's see, what is the probability of your friend going first?
1
out of 7. 7?
Still 7 people.
1, 7.
So,
There's 7 people going.
there are 7 people going. We know that there's 5,040 ways that they could be ordered. So, what's the probability of our friend being first?
1, 7.
Probability
6 factorial.
friend
1.7.
first. Now I heard a couple of people say 1/7. Why?
Wait, when you
There's
go,
7 people and it's 1
Because we don't care about the people that come after.
wait, I have a question.
Yeah.
Okay, so probability of your friend getting first, is that different than the? Actually, never mind. I'm gonna ask this later when I figure out how to say it.
You mean different than this?
Yeah.
This
Does it have to do with that? Does it have to do like with 1 being in the front?
It has. Yeah. It kind of does. Because this is the total possibility, so this would be the denominator.
Okay.
And then we have to get a numerator that tells how many times our friend would be in the front.
Okay. How many different ways he could be in the front?
Yes.
Okay.
Yes. Max.
So basically, questions that deal with everyone will have a factorial, and questions that deal with just one person will have 1 over whatever.
Not necessarily.
About 1 17.
Not necessarily.
So that one would be like how many different combinations, and this one would be like what's the chance of getting a certain product.
Right.
Would this be 1.7?
Close. Close. So this, for those of you that are wondering about how this works this is now the total amount of possibilities that we could have. Total amount of possibilities. I want to know how many of those possibilities will put our friend first. It turns out that there are a couple of ways that you can look at this. We know that there are 5,040 possibilities of orders. How many of these will have our friend being first?
You have to do like one. Oh, do you just put, can you just put x over 5,040 and then 1 over 7?
We could, if we wanted to. We could.
Why don't you just do that?
We could also consider this. We have 7 people. How many do we want to choose to be first?
1.
Wait, is that right? Hold on.
No.
Let me think about that. Wait, no, that can't be right. Sorry. That's going to work over here, but not here. So it turns out that it's 720 over 540. But there's an easier way to do it. Look at this first number.
7.
Yeah, 7. How many friends do we have?
7.
7. How many times can our friend be here in front? Could be 7. But we have 1 friend, so it's just going to be 1 out of these 7. So really this is just 1, 7. So it's really just 1, 7. Because out of those 7 possibilities in front, we can have 1 of them.
Is that just 6 factorial?
720 is 6 factorial, yes. Yes.
Would that be permutation? Would that be a choosing
Combination.
combination? Yeah.
Switcher. Yeah. This would be a combination. That would be a permutation because their order matters. Here, order doesn't matter. We're just picking one to be in a certain spot. It'll make more sense when we do this one. Okay, so now we have 4 friends out of the 7. Okay, so out of the 7 people that are going to perform, we have 4 of them are going to be our friends. What's the probability of the first 2 performers being our friends? Okay, here's where it kind of gets interesting. Because we have to consider the number of our friends being... Hi.
Needed attention.
Oh, Saturday's here. See you later. So, number of our friends being the first 2. So that's what we have to consider. The number of our friends that are the first 2 out of the number of performers being the first 2. Okay, so the number of successes will be the number of our friends being the first 2. The total that we're looking for is the total number of performers being the first 2. Now, it could be the first 2, it could be the middle 2, it could be the last 2, it could be any 2 whatsoever. So, does order matter?
No.
Not really. Order doesn't matter.
So it's a combination.
Yes. So, since order doesn't matter, we're going to be dealing with some combinations. So, let's look at the number of our friends being the first 2. Since order doesn't matter, we're going to be using permutations or combinations.
Combination.
Okay. And we're taking out of how many?
2.
We want 2, so we're going to choose 2 out of, how many friends do we have? 4. Okay. Divided by the number of performers being the first 2.
7.
7, choose 2, nice.
Also, we choose 2.
Yes. So out of the 7, we choose 2. Those are the total number of performers that are going to be the first 2. And then out of that total, we have to look for the number of friends that we have that can be the first 2. Since we only have 4 friends in there, it would just be 4 choose 2. Okay, so now that we've put these down, from here it's just academic. Actually, it's more algebraic. So 4 choose 2. What do we do then? How do we do that with factorial?
4 factorial minus, over 2 factorial.
2 factorial, and then
You cancel,
not yet.
write it out.
It's another 2 factorial. Because not only do you put the number there, but you also have to subtract. Goes there. 7 factorial over.
2 factorial.
Perfect. And then from here, it just goes into your calculator. So you got 4 factorial, which is 4 times 3 times 2 times 1, divided by 2 factorial, which is 2 times 1. The 2 and the 1 cancel, so you get 4 times 3 on top, divided by 1 times 2 on the bottom. What is that?
6.
Thank you. And then we got 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, divided by 5 factorial, which is 5 times 3 times 2 times 1, which leaves 4 times 3 times 2 times 1, thank you.
Probably the only time I'm going to correct you.
I got it, we'll see. Which leaves 7 times 6 on top, divided by the 2 times 1 on the bottom, plus 42 divided by 2, which is?
21.
Good. And then we reduce that. Close.
2 7.
7, yeah. So the probability of our 2 of our friends, going up there and being the first 2, is about 2 out of 7. About 2 out of 7. Not to say that it always works out that way. Could be a tile, because there's a tile fish. Alright, so 2 out of 7. Again, this is theoretical probability, and in theoretical probability, yes.
Okay, so I did differently, and I want to know what I did wrong because I got a different answer.
Okay, I'll be there in a second.
Okay.
So in theoretical probability, oftentimes we use the choose function. So we're going to use the choose function to get our answer. Yes?
What did she say? It sounded important to you.
Oh, she got a different answer, and she wants, because she did a different process, and she wants to know where the process broke down.
Oh, I see.
Okay, so let's talk a little bit about experimental probability, then geometric probability, and then we're done.
Oh, I got it right. Never mind. I just weird man.
Oh, okay, good. Let's see. So I'm going to erase this, and probably this one. Okay. Experimental probability always starts with, guess what? An experiment. So I went out and I asked 30 people. Random people.
Did you actually?
I'm not on this. Maybe. Maybe not at the same time. I asked 30 people this question. At what age do you want to die? Now, I'm not saying that I asked him that purely for experimental purposes. I would say at least 25 of those people had pissed me off beforehand. Yeah.
So they're not gonna.
So then now I have my list. It was supposed to be. It was supposed to be like sinister laugh. So I could just be like Linda Heiko. Alright, so at what age do you want to die? And here's the results that I got.
I bet it's 90. That's a good year to die.
Is it really?
Yeah.
Really? I had
30 years old?
Sorry.
What? What?
Why would they
No
want
way.
to die? Hey.
These are all
He's
not real.
He's
He's doing it for the sake of math.
This is stupid.
For science.
I got that.
Haha, I got it.
So, no, what if the camera's been off the whole time?
Jeff
It's
got
on.
It's not.
Jeff the Bob.
It's not.
Don't know.
It may happen. If the battery is almost out.
Okay, so 2 people said 30 years old, 3 people said 40 years old, 2 people said 50 years old, 10 people said 60 years old, 7 people said 70 years old, 2 people said 80 years old, and 4 people said 90 years old.
No way.
Wait.
Oh.
Yeah, it turns out most people wanted to die at 60.
Why would you die at 30? You can't be president.
True. But a lot of people think that they're here for a good time, not a long time. So they just think that they'll wear themselves out and die by 30.
So the people you asked, the 2 people that said 30 years old, were they just, in the clouds?
They were just
Were
bored.
they weird people?
They were kind of weird people. Actually, they were not necessarily weird. They just really thought that they were going to die by 30. You know, some people get an idea, some kind of notion in their head that they're going to die at a certain age.
Maybe they had a vision like that's so
really
random.
thinks
It
he's
happens.
I have some of those.
So probability of 40 years old. Probability of at least 50 years old. Probability of less than
What'd you say?
70 years old. Probability of older than Marenco.
How old are you? That's like 400.
Franco, you're like,
Aren't they all?
you're like a day over 19.
Oh, thanks. Probability of older than or older than Sun Ho, since he's got the camera.
Oh, somehow.
Oh, I'm going to go home and I like. Oh yeah, they talked about.
Alright, so I want to know the probability of people who said that they want to die at 40 years old.
Okay.
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 I know you're probably thinking to yourself,
Or 110.
you think 110?
40, just kidding.
It's 110.
You think it's 110?
Yeah.
Why do you think it's 110?
30.
Oh. So out of the experiment,
Yep.
how many people said 40 years old?
3.
Out of how many did I ask?
30.
Which is how they got 110. What about the probability of at least 50 years old?
2 out of 30.
25.
2 out of 30.
25 out of 30.
5, 6.
So I heard 20, I heard 2 out of 30, I heard 25 out of 30,
It's anything about
I heard 115.
It's
25.
25.
How many do you think it's 1/15 or 2 out of 30? How many do you think it's 25 out of 30 or 5/6? Okay, why do you think that it's 25 out of 30?
Because it's right.
Will you take out?
Because you take out the 5, the first 5.
So we take out the first 5. So we're left at 2 plus 10, 2 plus 10 is 12, 19, 21, 25. Because remember, at least means there or more. So it's 25 out of 30, which is 5/6.
Whoa, okay, okay.
Awesome.
You offend me there.
What about the probability of less than 70 years old? Less than 70. So we'll count 70 and we'll go back. We'll count 70 and go back.
17 out of 30?
17 out of 30?
Yeah.
Because we're counting 70 and going back.
Oh, then that's
So you take out
24 out of 30.
How much? Oh, okay.
Okay.
So,
Why are we setting that?
so less than or equal to. So you said 20 what?
24.
24.
Okay, because we have to count everything from here up. So we got 7, 17, 19, 22, 24 out of 30, which reduces to?
No, less than that.
12, 15.
12 fifteenths, thank you. And reduces to?
3/5.
Nice. Really?
Yeah.
Yeah.
No. Isn't it
No.
4/5?
No, 4/5.
4/5.
Take out.
Because we divided by 3.
Yeah.
Easy to make sure that. What about the probability of people who want to die older than me?
How old are you?
Wow.
4. I'm going to be 35 this year.
So that's
Okay, so I need 45.
Okay.
so 28 over 30.
Okay, so 28 over 30, which reduces to?
14 over 15.
Alright, so 14 out of 15 people want to die older than me. That's good. What about older than Sun Ho?
30 out of 30.
How old is Sun Ho?
30.
Me and Tian turned 16. Oh, no, he turned 16.
I already did it.
You already did it? You died before?
Wait, you just
Older
heard
than
me?
him?
Oh,
older than this.
So yeah, how many people want to die older than Sun Ho? Older than Sun Ho, I think is what?
We got a birthday
18?
yesterday.
Oh, I'm already
17. Older than him.
17?
Yeah.
So
Oh.
how many people want to die older than Sun Ho?
30.
30. Out of?
Yeah.
Which is?
How old is he?
100%.
100%. Exactly. Last one.
Wait.
He's
Birthday.
in the 15 yesterday.
Yeah.
Wait,
I've got a target. This is my target.
Did anybody say I wish I was dead already?
No. Well, they did, but they died.
I wish I was dead. That sounds horrible.
I want to live
I wish I was dead.
Okay. This one is going to be diagonal stripes. This one's going to be polka dots, or just dots. This one is going to be vertical stripes, horizontal stripes.
No, you passed
That's the target.
You guys got that out?
Yep.
Put a bounce off the reaction.
Okay. Here we go.
I wish I was dead.
I'm going to take this marker. I'm going to throw it at the target. Assuming that I hit the target. That's a big assumption too, because I missed both times I threw the first period.
making your target at all.
You missed twice.
Well, we could do that one. After we learn the concept of how to do it.
What if you break
Yes.
the whiteboard?
Alright, here we go. Assuming that I hit the target, here's the question. What is the probability of hitting the dotted part?
35.
So the probability of hitting
Oh,
the
wait.
dotted part. Here we go. Ready?
No, it's less than that.
Yes. Yes! I hit it! Finally.
Close enough.
Sorry. I didn't hit the dotted part, but I did hit the target. So assuming that I hit the target, what was the probability of me hitting the dotted part?
7/33.
Whoa, 7/33. Interesting.
You just look at area of the whole thing.
So, how did Marcos come up with 7/33? What fraction did he have before that?
The area. Oh. I don't know.
Earlier he said something about 35.
35. You do 15 times.
It's 35
15 times 30.
What is it, 165 or 176?
I think it's 176. Let me do that again.
So, how are we doing this? How did he get to
The area of
35?
the whole
The
thing.
area.
So
The
it's
area.
15 times.
The area here is 35. This one is. This one is.
48.
Thank you. And then this one is. Okay, let's see. So 42 plus 48, that's 90. 90 plus 40 is 130. 130 plus 165 is. Or sorry, 130 plus 135 is 165. So 35 is area. Area of dotted over whole area. And this is geometric probability because we're taking geometry. We're using geometry. 35 out of 165, he reduced that, divided both of them by 5 to get 7 out of 33. Now, what's the probability of hitting the diagonal stripes?
40 out of 165.
So, give me the area of the dotted, or the area of the diagonal stripes. Yeah? Is it 40? Yeah, 40. Over. Reduce that, that would be 8 over 33. Yes?
How do you get the whole area again?
We took each little area and added them all up. Or you could have done 15 times 11. And that would have given you 165. So geometric probability deals with area. Experimental probability deals with an experiment that you did.